Okay, should we get going?
Yeah. 103, just like I said.
103. Okay, well, we can trim the video later for posting it online. So, welcome everybody to this early afternoon tutorial series. Do you have any words of introduction or not?
Ryan Gerson is going to take it away.
Today we're going to show everyone how to use Omfit to view transp runs and also to create transp runs for your own analysis. So a lot of people may ask, what is transp? And so I've written down here a very simple description. So in its simplest and most common form, transp is what we call a power balance code in the Fusion tokamak community. So this means that transp takes the measured quantities, things like the equilibrium, the plasma profiles, and also the sources, such as the particle recycling rate, the heating, and torque. And it computes things that we call confinement quantities or transport quantities, such as the total energy confinement time, or profiles of the particle heat and momentum diffusivity. So in all its glory, though, transp is much more than that. It's a comprehensive, time-dependent, general geometry, interpretive, and predictive simulation package. It's one of the most popular and well-known tools for interpreting tokamak discharges and predicting the performance in future experiments and future devices. So what we're going to talk about today is essentially summarized in a recent Fusion Science Technology article that was written at one of the more recent IEA technical meetings. And that's what's shown here on the screen of my laptop, which is a recent paper in FS&T about orchestrating transp simulations for interpretive and predictive tokamak modeling with Omfit. And so this is what we're going to go through today. In terms of the overall context and where does transp fit in all of a tokamak and whole device modeling, seen here is what we call the Death Star image of the core edge boundary disruption and experiments, verification, validation. And transp right now is mostly fitting in the context of a workflow manager on experiments, verification, validation, and advanced reduced models of the plasma core. So I'm going to start off with showing you how one can view a transp run, because this is most people's introduction to transp, is that someone else has already performed a transp run for them. So I'm going to start with Omfit. In the previous videos, we've seen how Omfit can import a physics module. For example, if you go up to File and Import Module, gives you a long list. And you will see that transp is one of the many that is there. As this is somewhat slow, there it is. Transp, you'll find it here. And a description, short description over here in terms of keywords, and then a long description. And there are citations here as well. Typically, when you import transp, you can double-click on the module, and it will open the graphical interface. And so there's a number of fields here for the user to enter, such as device, which here is D3D. You enter the shot number. Here is a D3D daily reference shot. And for transp as a standalone physics module, you only need to enter the start time and the end times, as it says up here in the top. And then you'll need to enter a transp run ID, which is a letter followed by a 2-digit number. And I will first show you an analysis run A35, which is one I did some time ago. But before we get into transp, I just want to introduce you to the discharge that we're going to be investigating. The discharge is shown here in this figure in the Fusion Science Technology article. This is what a D3D daily reference shot looks like. It is a inductive scenario. It starts off in an L mode phase, followed by a power ramp up, shown here. In gray is the neutral beam power, and then smooth is in blue here. It enters H mode and is an LME H mode that then has sequential ramp up in the auxiliary heating power from neutral beams. This is the discharge that we're going to be investigating for this worked example. One question that a lot of people have is, well, where's the data coming from and where's the data going and how am I actually interacting with the tokamak data? This is shown here in a graphical flowchart representation where the tokamak data, at least for D3D right now, most of the information is coming from the MDS Plus archives, where it's coming from a user's analysis. The user has done equilibrium reconstruction or they have done profile analysis. Omfit orchestrates everything in terms of the equilibrium, the profiles, the time histories of the heating and current drive systems, and then all the various settings. Transp is driven by a name list, a Fortran name list, and you'll see that there's many, many, many options. So the user here is interacting with Omfit. Omfit prepares this equilibrium profiles and settings, sends the data to the Transp grid, which is at Princeton on the East Coast, and that's where all the computation happens. And then the data is written back to an archive, which at D3D is MDS Plus, which is then read into Omfit for visualization or passing on to other workflows. Transp in itself is a very powerful tool for investigating plasma performance, but since it's been around a very, very long time, many other codes use a Transp output. For example, we've been doing a lot of gyrokinetic modeling, and Transp output, in terms of the power flows and everything, is extracted and then passed off to those other tools. So the first thing I want to do is I want to investigate an existing shot that I've already analyzed. And so I just want to show you what you can see when you have an existing Transp run, and then I'll go on to preparing a Transp run. Kind of start with the end product, and then I'll show you how we create it. So this is the graphical interface, and this is what it looks like when Transp run exists. This is Transp run ID 163303835. There's a number of buttons that are always here for you to check the status of a run or open the Transp website to see the status of your run. But down here in the main GUI, there's a number of options here. The first one is a run plot, and this allows you to view and visualize an existing run. For example, we can search here for a scalar function of time, or a function of time and space, or what Transp calls multiplots. But one of the most instructive plots is this one here that says compare to experiment. So when I click this plot, a series of graphics will show up, and these graphics show a number of common quantities that people look at after a Transp run is completed. So for this example, we're showing the measured neutron rate is in blue, and the total neutron rate from Transp is here in purple. You can see it's low early on, and then it picks up as the beam power increases. The beams are all modulated. And you can see here how these things are modulated in time. You can see that the neutron rate reasonably well captures the experimental neutron rate. Here you're comparing purple and blue. There's also things like the total plasma stored energy, which are typical plots that people usually want to look at to see if your plasma profile analysis is consistent with what comes out of Transp. Here you have things like the EFIT stored energy, which is in blue, and the total Transp equilibrium energy, which is yellow. The cyan color here is the thermal energy, and here's the beam pressure. Okay. Transp also has a number of other outputs, including diagnostic simulations. So when you analyze an entire plasma discharge, you can do things like simulating the MSE pitch angles, which I can show here. This one has a pitch angle simulator. And I can look at the time evolution of the measured pitch angle and the Transp one and see if there's any deviations. This last plot shows an example of all the pitch angles from this shot. And this allows you to tell how well Transp captured the evolution of the magnetic field. There's a number of other options, including plotting things like the the line average density from the various interferometer chords that are on D3D, which are shown in this graphic here, where you can see that my Transp analysis is very well matching the measured line average densities.
So it's my understanding that the profiles of density are an input. So why would I expect that the line average density would be different?
Well, the line average density here was used as a constraint on the Thompson scattering that was fit, right? So it might not exist, it might not match exactly, right? And so this just tells you how consistent they are. If you want to look for any systematics in the analysis you did versus the way that TRANSP interpreted your analysis.
There's also the possibility that you didn't do an analysis run. You did a
that's right.
predictive run.
So if you do predictive runs, perhaps you want to feed back on the line average density. So you have a programmed line average density, you want to see how well TRANSP matches your program. That's another way of doing it.
And these plots are specific to D3D. Are there similar plots for other machines?
There are. For NSTX, there is a similar summary compared to experiment. But the MSC system right now, these are specific to D3D. But what is general for all machines is all the variables that exist in a TRANSP output. So TRANSP has an enormous amount of output that you're able to search for. And some of the example outputs here can be shown in the rplot functionality, which is another way of viewing TRANSP outputs. This allows you to compare different machines, different TRANSP runs, in terms of looking at the history variables such as the total energy confinement time, which would be an example here. The beams are modulated, so you see a lot of oscillation here, but it's very clear when the plasma goes from L mode to an H mode, you see about a factor of 2 increase in the energy confinement. And also provides comprehensive visualization of plasma profiles. So here I'll just plot one of the inputs, which is the electron density. Since everything is time dependent, everything is visualized with space and time maps. So there's a lot of information. This will take a second to plot.
Is there a list of variables?
There is a list of variables, yes. So here's an example of the visualization of a two-dimensional data field, which is going to be the electron density as a function of the spatial coordinate rho, the square root of the normalized toroidal flux, and also in time. Maybe I shouldn't have done that. It's going to take a second to render with this
Jump
one.
to the main GUI and
Okay.
show the other tab.
Okay, I'll just skip that for now. So if you ever want to search for something, you can always type in here like a scalar function of time. If I type energy, this will reform, and it'll give me a list of all the quantities that either have energy in the name or in the description. So there's also other things like these multiplots. So for energy, these are all the different multiplots. You know, rotational energy inputs and ion energy transport, a number of things like that. There's way too many outputs for you to simply just list them out and search them. Okay, so a lot of times when you're working on tokamak, another user has done TRANSP analysis for you. But really what you want to get to is you want to get to the point where you're able to do your own TRANSP analysis and simulation. And so I'm going to demonstrate here how to prepare and submit a TRANSP run for this D3D reference shot. And then I'll describe how TRANSP is a component in other workflows. So fundamental to TRANSP is defining what your TRANSP run ID is. And so for this example, I have written down that for the TRANSP tutorial, many people have gone through it. There's an online tutorial, this is a Google Doc, and we're up to tutorial number 32 as the next available run ID. So many people have gone through and done the TRANSP tutorial.
There's a button there you can press to check and see if runs are available.
That's right, that's right. So you can see successful TRANSP runs for this run ID. This has a T. I'm not going to click it because it'll run through like 35 different ones, and it'll output to a text file the description that the user entered when they did that TRANSP run, and then you can view it, because otherwise the log in the terminal will be super long. So I'm not going to do that right now, but you can always click this button to see you know, what are all the successful TRANSP runs for this ID. Or if I were to use 31, which is an existing run, I can say I want the next available run ID. And so when I click that, yeah, it finds 32 as the next available, which I happen to know because before coming here I searched for it. All right, so now we're going to go through setting up a transp run. And what we're going to do is we're going to use basic equilibria and profiles that are already constructed. They've already been processed and they exist for D3D as the between shot type of normal analysis. And so here we go. The first thing that you want to do typically is enter a comment. Tutorial for Omfit guides. Every transp run has to have a comment. It won't let you submit it unless you provide a comment. So try to provide something meaningful. So with a completely blank transp module, the first thing that we do is we load the transp name list. And so when you click this button, load transp name list, actually I should reset this. Please stand by. I'm going to reset the module because I was testing something. I've reset the module, and now it's a completely clean and fresh transp module. The first thing I'm going to do is I'm going to load the transp name list. And one of the powerful things about running transp through Omfit is that we're now doing this on multiple different devices around the world, including domestic devices such as Alcator CMOD and NSTX, but as well as devices overseas such as Jet, ASDAX, MAST. And so what happens when I click that button is that a input name list is created. So in previous tutorials, we went over what is the Omfit tree and what is the data that exists there. What you'll see here is a transp name list that was created as the inputs. And this is a long, long ASCII text file that is set up in the same manner as the transp online help. And this is a transp name list template. And so Omfit interacts with this name list by turning switches on and off, setting things like the time ranges or the time steps of the transp run. And you can see here as I page through, there are multiple sections with full descriptions of what all the variables are, what they do, and what their values are. If you want to dig into the details, you'll see that the name list is broken into many different sub-name lists. So for example, under transp, it has the MPI control. It tells you whether or not you're using parallel processing for things like the neutral beams or for predictive transp. There'll be things like the magnetic settings in terms of the equilibrium geometry, the settings for N-class, neoclassical, and a number of different options. You'll see here the list is quite long because transp is able to handle a number of different models for sources. So once we created that name list, we're now going to load equilibrium U files. And you can see these things here are numbered. There's load transp name list, load equilibrium, load the profiles, and then we'll load the ones that are specific to the device, to D3D. So we're going to load the equilibria between the times that we've selected here, between 2900 and 5000 milliseconds. So when I click this button, Omfit's going to gather all the information about the equilibrium. It will log into a worker node here on the Iris workstation. And it will now begin to compile all the information from MDS Plus through a transp utility called the scruncher that takes a 2D map of the equilibrium flux surfaces. It does a Fourier moment decomposition and stores them in the Fourier moments in some ASCII text files that are called U files. So this will just take one more second. You see that it's stepping through. It checks to make sure all your equilibria are reasonable. And it's now created a whole number of new input data. And all that new input data is stored over here under U files. So for example, over here I have the current U file. So if I type return, you see that it will plot the plasma current in amps as a function of time in seconds. We can also go over here to view and modify the U files. So here I can smooth or do whatever I need to do to process my data if I need to do anything. So now that we've loaded the equilibrium, we're going to load the profile U files. And for this example, I'm going to take the profiles all from what we use as between shot profile processing. It's called ZipFit. And I can click here and simply load the plasma profiles. You can see it's quite fast. And so now you see a number of new U files have shown up here, in particular NEL for the electron density. And you can see here is a 2D space and time color map of what the electron density profile looks like in this case. You can zoom and do whatever you want to view the space and time history. The same thing exists for the electron temperature, ion temperature, rotation, impurity content, et cetera, et cetera. So now the last thing you need to do is, every tokamak's different. They have different heating and current drive systems. D3D has a lot of neutral beams, but we also have electron cyclotron heating. Other machines will have lower hybrid, they'll have ICRF. All those things are very specific to that machine. And so for each tokamak, the responsible officer on that machine has provided the Python scripts to prepare those sources and to make them consistent with the trans nameless settings. So now here for D3D, I'm going to say load device-specific U files and settings. This is going to get the total plasma recycling rate from a calculation that was developed here at D3D. It'll get the total neutron rate, which is also something that's specific to this tokamak. And then it will get the time history of all the different neutral beam sources, including their geometry. So that is, of course, very specific to D3D with co-injected, counter-injected, off-axis neutral beam injection. And so then this will just take a second to process. And as this runs, I just want to take a brief moment and detour back onto the flow of data. So that way you don't get lost in terms of what we're doing. What I'm showing you is I'm simply clicking the buttons, and it's easy to come in and just click button 1, 2, 3, 4 and say run. But what actually happens to that data? What data is actually required? Where does it go? How is it used? And so you can view this flowchart on the TRANSP website. If you want to go there, there's a document there that describes the equations that are used in TRANSP. And so what I'm going to show here is simply the input data that is typically required, and this is all for interpretive TRANSP analysis. The input data is typically the plasma current, which I already showed you, the surface loop voltage, the plasma shape, so the shape of the flux surfaces, and whether that shape is evolving in time, whether it's getting smaller or increasing. The radiated power, fits of the electron density, electron temperature, ion temperature, and the plasma Z effective, or a single impurity ion density. Now there's two high-level ways of running an interpretive TRANSP run. Either you can use the full equilibrium that either you created or is automatically generated for the tokamak that you work on. And that means that the shapes and the internal current profile is all fixed. It's all created by a code like EFIT. The other way to do it, so that's called Q analysis mode. And in Q analysis mode, the output quantity is the plasma resistivity. The other way to do it is called magnetic field or colloidal flux diffusion. So here the plasma current evolves resistively, where you've given it the electron density and temperature and Z effective so it can calculate the plasma resistivity. Then as TRANSP moves forward in time, the current evolves, Q will drop and undergo sawtooth oscillations if it gets too low. And then the output quantities are going to be the current profile, the Q profile, colloidal field, the plasma toroidal voltage profile, and optionally the plasma Z effective. So that's two high-level ways of running TRANSP. I believe later in this series we're going to have some kinetic equilibrium reconstruction tutorials. And for that kinetic equilibrium reconstruction, one must perform a resistive current diffusion analysis to get the total plasma current as it's driven by ohmic and bootstrap and any non-inductive sources. So the first step the TRANSP will do is a neutral transport for particle balance. So here the recycling and the fueling from beams is input to calculate the total particle flux. So that particle flux and particle balance then goes into the convective terms of the ion energy and momentum balance and the convective term of the electron energy balance here. The neutrals also go into charge exchange losses here in the momentum balance equation. Then with both the ion and electron energy both the ion and electron temperature profiles measured, we can evaluate the electron-ion energy exchange that goes between these two, and then output finally the total conducted power, the total conducted momentum flux for the ions, and then the total electron conducted flux. So the output here is going to be the particle flux and the particle diffusivity, the ion energy flux in chi-I, the momentum flux in chi-phi, and the energy flux in chi-e. I should have also noted here that the ohmic power will be slightly different whether you use Q analysis or resistive diffusion. So the ohmic power comes into the electron energy balance as well. So that's the overall flow for how the information processes through TRANSP to the typical outputs of things like chi, which is something that people typically are interested in. So now we've loaded all of our device-specific U files and settings. You can see here in the terminal it checked whether gyrotrons are firing, and so they reported no power because there was no ECH here. You saw that the neutral beam information had been written. So the next thing you want to do is set the TRANSP mode. And as I showed before, the TRANSP nameless has many, many, many options. So I'll go back and just give some examples here. That if you go down here and you look at the neutral beam name list, it has a very long list of all the different parameters. Okay, and rather than asking the users to learn about every single input nameless variable, what we've done in Omfit is we've come up with a couple of different predefined TRANSP modes. So I'll start with the first mode, which is the beast mode, and that stands for between and amongst shots TRANSP. And it was originally designed to be fast enough to run to inform experimental campaigns. So it is the most stripped down possible version of TRANSP for just looking at globals, things like the total plasma stored energy or the neutron rate. We've used this recently for D3D experiments looking at energetic particle transport, for example. The next mode is called analysis mode. And when one selects analysis, you can set the TRANSP mode here. And it'll set a number of settings in the name list. The analysis mode is the standard 10 millisecond time step, high enough fidelity for accurate particle energy and momentum balance analysis. And this is the way that is typically used if you want to look at, say, thermal transport in the D3 discharge. The final mode, okay, so the next mode then is going to be kinetic EFIT. And the kinetic EFIT mode is a resistive current diffusion, like I was describing before, but the neutral beams here are set at reduced fidelity to make the execution of the code much quicker. You don't need real detailed energy and momentum balance in order to simply perform a kinetic equilibrium reconstruction. But this mode does have a relatively fine radial grid of 100 points, so you can accurately get a bootstrap current near the plasma edge. And then the final mode we call energetic particle or momentum transport mode, which is very, very high fidelity on the Monte Carlo new beam package to accurately get the fast particle distribution and the torques and part of the plasma. That mode takes the longest, is not typically run. So let me go back and I'll just do an example here.
Now, if people forget, there's that question mark, right?
Oh yeah, that's right. So so there's these question marks that pop up along the way. And so here, if I click the question mark, it says, this is how you set up TRANSP for common analysis tasks. So like I said, analysis sets radial and temporal resolution to be typical for the given tokamak. So that mode is actually different for NSTX and JET and D3D. We've tailored them all to be the most appropriate to those devices. BEAST is very coarse in space and time. And kinetic EFIT sets the radial resolution to 100 zones for the bootstrap current and time stepping for typical equilibrium reconstruction. So now that I've clicked button 1, 2, 3, 4 and set my TRANSP mode, I can prepare a TRANSP run, which is going to be tr start, I think. Oh, of course. Like I said before, it's going to say provide a meaningful comment, right? That error is supposed to happen. That is not an error. Example for Omfit tutorials. And I'll prepare my TRANSP run. What this does is this takes all the data that is stored within the Omfit project here. The name list is mostly the name list and the U files. It will log into a worker node here on the Iris workstations. It will set up your path to make sure that it knows where the transp utilities are, such as tr start and tr send. It will create a tar.gz package, which then it sends to transp. So this is then performing exactly what, I think it'll ask me for my password, maybe not. I think it's working. So this is the part where I'm having prepared all of my input data. I'm sending it to the transp grid at PPPL, where it's going to run this. And I'll go back, and it'll say it's sending the run and communicating with the remote server. And in a moment, it should change the status from sending the run to waiting for the run to complete. So as that transitions, I will start to describe some of the options for the input name list for transp. So like I described, there was a very long list of options for running transp, and we've broken it down to a series of tabs that the user can traverse here. In terms of the time stepping, the overall time range of the transp run is set to be slightly wider than the analysis range here. So I said I'm going to start my transp run analysis at 2900 to 5000 milliseconds. Now transp is causal, and it runs in time-dependent mode by default. So at 2900 milliseconds in my D3 discharge, I already have had neutral beam power and ohmic power. The plasma current is already ramped up, and I'm starting my analysis in the middle of a shot. And so I want my analysis to be valid at 2.9 seconds. And so what we do in transp is we say, okay, your first valid time slice is 2.9. So let me go back a couple hundred milliseconds and start my transp run earlier. So I'll start it earlier. I'll start evolving the heating and the current evolution, if I'm going to evolve the current, in such a manner that at 2.9 seconds, I have a valid power balance. So now I can quote my thermal conductivity at 2.9 seconds because I always start my transp run earlier than my first analysis time. This is something that people tend to have a hard time grasping, is that you can't run transp in a single snapshot, that it runs time dependently. So if you want your analysis to be valid at a given time, you need to start transp earlier, because at 2.9 seconds, you're starting transp with zero heating. So there's no power flow. So your confinement time is infinite. And so your analysis at 2.9 seconds is invalid. You always have to start earlier. And we always run transp slightly later than the time slice that you have chose, because transp will not output exactly on a uniform millisecond time step. It evolves based on a predictor corrector algorithm to maintain high accuracy in the particle energy and momentum and current diffusion equations. So in terms of time, you have things like the input, which is a 20 millisecond input time resolution, which is the time resolution that I did my profile analysis on. You have the output, which we're also going to output on 20 milliseconds. These other ones you don't typically need to look at. These are things like the initial equilibrium and then the maximum time advance. For this is a beast run, so we're only using a coarse value of 20 radial zones, but for kinetic equilibrium, you might want to use 100. You can look at your equilibrium settings. So here I'm using a full input equilibrium. So all equilibrium info is taken from the U files. But the user can also set the TEQ inverse solver, or TEQ for colloidal field diffusion, or a free boundary isolver equilibrium. And there are things like the magnetics, where you can enable or disable the current evolution, which I was showing before in the flow chart. So now we can come over here to the plasma. You can see we have tabs for the plasma composition. You see that this is a deuterium plasma. The impurities is carbon here. And Z effective is taken from an input Z effective profile, but there are a number of different options. There are a number of options for the fusion products, ion temperature. The user can provide anomalous torque from 3D fields. You can do rotation prediction rather than rotation analysis. Or if you want to go all the way in, you can use a predictive transp solver and use a comprehensive transport model like GLF23 or TGLF or the multimode model. There's a number of options for the heating. So you can drive new beam from the shot, or you can design your own neutral beam heating. You can plot the new beam inputs or change any of these number of these options. You can use anomalous fast particle diffusion, which is a very common thing required for alpha and eigenmode transport. There's a number of diagnostics like simulating the MSC pitch angles or the CO2 interferometer. And you can also output much more comprehensive things from TRANSP than just 1D and 2D outputs. You can output things like the fast ion distribution function, which is very popular for energetic particle studies. And so that's the basis of basic TRANSP analysis through Omfit. And are there any questions about that at this point? I'd like to pause and see if people captured this, or next I can talk about how TRANSP can be a component in other workflows.
So just to be clear, if I want to do momentum balance, but I want even more grids than the default,
yeah,
what do I do?
So typically for a high fidelity momentum balance, you'll need to increase the Monte Carlo statistics on the neutral beam package. So things like the fast particle J cross B torques depend on the orbits. And so if you wanted to have detailed orbit following of those torques, especially near the plasma boundary, you'll need to have a finer radial grid, and you'll need to use a higher fidelity neutral beams. So one way you can do that is to go into the input name list. Well, the obvious way to do it is to come in here and change to momentum transport mode. And when I set this mode, it'll change a number of settings.
Well, I guess I meant more like, say we're in beast mode,
yeah,
and I want even more beastie. Do I go in and
more
change the radial grid to 15?
The way that I would do it, probably, still, TRANSP right now is time limited by the ability of NuBeam to calculate the Monte Carlo heating and torque deposition. So one can come in here to the heating and current drive package, and rather than using the neutral beam predefined fidelity, you can do things like change to expert user. And when you change to expert user, you can set some of these options, like change the what's called the orbit acceleration, or reduce even the number of Monte Carlo particles further than 1,000. Or you can add more MPI cores. You can go and run a low number of NuBeam particles, but use 16 CPUs to make NuBeam run even faster, make it even more.
So if I click on that, it'll change the nameless file in the tree.
That's correct. So when you come in here, let me pull down the name list. So TRANSP under MPI, pserv is 0. If I change this to say 8 cores, it'll change this to 1. And Omfit will then know under the settings, physics, MPI, this variable TR MPI, which is the number of NuBeam cores that I want to use, is then set to 8. So this is the way that the module is broken down. As I change this,
that gets specified in the sending.
That gets specified on the sending. So you need to know when you prepare the TRANSP run, when you do what's called TR start, which creates the total package that will be sent to Princeton. It needs to know whether or not you will be using MPI, parallel processing, and that code will ask you for the number of MPI cores. And Omfit knows how to answer that question. And so it gets it from this field here, MPI. So you can use MPI for NuBeam, which is called TRMPI. You can use MPI for toric, for ICRF. And you can use MPI for predictive transp. For example, if I wanted to use the TGLF transport model, rather than inputting my plasma density and temperature, perhaps I want to design a shot. So I want to use a transport model and modify the heating, for example, to say what happens if I add electron cyclotron heating to this D3D discharge. So for most users, they won't need to dig into the details. If you're simply using trans for analysis of your existing experiment, you want to know if you have any systematic errors on your plasma electron density or temperature, plasma impurity composition. We have the capability to scan the input variables. If you would like, you can scale them or scan them easily in the trans module. But this is the way that most people would perform a interpretive transp analysis. And so then, you're off and running, because there's a very wide variety of applications for transp analysis. And we're trying to make sure that people are able to do this in a fairly seamless way. So that's the way that transp operates as a standalone package. I'm just going to abort this. I don't need to wait. That's the way transp operates as a standalone module. Yeah, question.
This is an important question. Is it okay to abort that? What happened to your transfer right now?
Oh yeah, okay. So that's a very good question. Once the transport is sent to Princeton, it runs on the trans monitor, and so I can open this website. It's essentially now disconnected from Omfit. So Omfit is the thing that orchestrates the preparation of transprons. But once the transpron is done, once it's sent and is running, it will then finish regardless of what you do with your Omfit project. I can delete this Omfit project, and the transpron will still complete. It'll still write back to MDS Plus here at D3D, or it'll write its netcdf file at transp, and people at JET will copy it. And so if I look in this website, this is the transp grid monitor. You can see a number of different transprons that are running all right now. You can see that there are many, and here is my transpron. So here it's I started the transpron at 2.7 seconds. The restart mark is still there. It'll be progressing, and as it runs, this will progressively update until the transpron's finished. Then you'll get an email to say your transpron's done, and then when you open Omfit again, the graphical interface will now be not prepare transpron, but view transpron, and you can view the transpron just as I showed before. So then that's archived essentially forever.
Brian, this is Darren. I had a question. Yeah. So what if you want to use, I'm always used to editing the name list by hand. So what if you want to do that? Is that possible?
Absolutely. That's a very good question. This is something that a lot of people want to just type in the name list. They're used to opening the name list in a text editor and searching it. So if I come in here and open my trans name list,
how do you do that?
Oh, sorry. I click on the entry in the Omfit tree, and then I hit the spacebar. And I have Omfit set up to use Emacs, which is the best editor.
Agreed.
All right, so for example, here's MPI, and I see MBI pserv is 1. And so I see over here in my name list, you see MBI pserv is 1. If I change that to 0, I can come in here, and if I right-click on this, I can reload this from the file, and you see that it changed it. So if you ever want to edit a name list using your text editor, edit it however you feel like you want to. You can add fields wherever you want. So if I search for N class, maybe I want to change, I want to change this from using Sauter to using N class for the plasma resistivity. I can certainly change that. But for the things that are already supported in the graphical interface, we kind of want people to use that, because in transp there are nameless variables that are conflicting. I can't use both N class and Sauter for the plasma resistivity. That doesn't make sense. And so in Omfit, it'll give you a selection that if you select Sauter, it deselects N class. It deselects all the other options, Spitzer, etc. And so by manipulating and orchestrating the transp runs through the graphical interface that has the built-in logic for conflicts, we're able to reduce the number of errors that we have when we send the run to Princeton. Because back at Princeton, there is a whole team of people that do triage. And whenever you have an error in your name list, they get an email and they go and look, and then they'll send you an email saying, here's the mistake that you had in your name list. And I think we've reduced the number of trivial nameless errors, syntax errors, these types of things, by preparing our transprons through this interface. And not every single quantity has a graphical element associated with it, only the most common ones. And we're very adaptable. We'll field requests, and if someone wants to make something part of the GUI, that's easy to do. Mostly it's emerged through the most common things that people want to change. So not every single thing here has a graphical interface associated with it.
There's also a middle ground if you aren't married to the Emacs editor, but you also don't find something that you want in the graphical interface. You can just go in the tree there, select it, hit tab.
That's right.
Edit it directly.
So if I come in here and I want to change how frequently Transp outputs its restart files. So for beast mode, I don't want to take time writing restart data. If the run crashes halfway through, it's relatively inexpensive. I can submit another one. But if I want to make it so that this is a very important run, I want to restart. I want to write restarts in case of a failure more frequently. I can change this to 10 very easily. So any variable that already exists can be easily manipulated, and you can easily add a new variable if you happen to know the name of that variable here through the interface. So yeah, that's right. There is this middle ground. Now once I submitted and prepared a transpron, actually all the information is also exists on disk. It exists in a project area on Iris that you can go in, and if you want to look at the name list and all the U files in their full glory as ASCII text files, you can go and look for that.
Can I try one thing?
Sure.
So,
Thanks. Oh, because you want to open the big nameless editor graphical interface.
That's right.
Yeah, there's a very large one, but actually, if you do that with the trans nameless, I think it takes up most of the screen. Okay. Which is why I don't typically edit it that way. But if I go to an area just for expert users, 1 second, trans. So here's all the different transprons that I've done. As you can see, there's quite a few. I think I want T35, was it? 32. So there I can do, in this directory is my trans name list exactly as it was submitted with all my U files. So if you ever want to share this information, it all lives there on disk. So as soon as you say prepare transport and send it, Omfit could, I don't want to say crash, but then you're disconnected, right? So Omfit has done the service of preparing the transpron, but then you can go and change the name list and resubmit the run however you want from the command line if you know how to do that, which is the way a lot of people know how to do it. Okay, we're getting close to an hour, so I'm just going to.
Can I ask a question?
Please.
This is Dayang from UCI. So I'm wondering if I want to use a different U file, for example, like a GA profile or Omfit profile instead of a zip file, how should I do?
Okay, so that's exactly what I'm going to show next, which is how Trans will interface with the other modules in Omfit. So one way that I can do it is that if I import a module, and say I don't want to use zipfit, I want to use Omfit profiles. which was demoed the last time. Typically, you would come in here and you would start Omfit profiles. You would, type in your times, choose your equilibrium, fit all your profiles, and then you would, now you're done with your profile analysis, you want to run transp. And so if I import another transp module, eventually, it's a little slow because I'm running on my development version, but that's okay. Now I'm just going to import another transp module called transp1. What you'll see here is that, in a moment, if I go for some run that probably does not exist, so I can see the prepare GUI. Now it does not give you the option for zip fits because it knows that Omfit profiles is in the project. It will automatically get your profile analysis from the other profile module. So the previous example, there was no other module, there's no other physics modules, only trans. So for standalone transp, it can only get equilibrium from MDS plus, and it can get profiles from ZipFit. But if you have the EFIT module or the Omfit module already loaded in your project, trans will get its information from there. And that is all set through what's called the module dependency, which is the glue that holds multiple modules together. Under dependencies, see it shows Omfit profiles, which says if Omfit profiles is here, then use its information. So it automatically knows about it. All you have to do is do your profile analysis, import the trans module, and when you click that button that says get profiles, it'll say getting profiles from Omfit profiles module. That's the way that they're connected.
So the button was grayed out now because you don't have the profiles in the Omfit profiles module yet.
Well, it was grayed out because I don't have a name list loaded yet. So you have to load the name. It still guides you through the steps.
Brian, I have a related question. So
Sure.
I look at the script. So it seems you can use either Omfit profile or kinetic EFIT, but it doesn't need the G profile there. So if I want to, for example, if I want to use a G profile fit.
Yes, it is there. Under dependencies, there's GA profiles for single time. There's GA profiles time, which is a time-dependent GA profiles analysis. There's EFIT, Omfit profiles, EFIT time.
Yeah, I saw that part, but when I look at the script there's it does not list the GA profile there.
Okay, well, I'll have to check on that. I thought that it did. Maybe it only supports GA profiles time right now. It's possible. I can check on that. So you can send me an email and I'll look into it. So that's a really good segue for how trans fits into other workflows. So when I come in to Omfit profiles and maybe I want to do a kinetic equilibrium reconstruction, which we're going to see at a future tutorial. When I come in and import kinetic EFIT, you see it's going to load a lot of information. So what we have here is EFIT time, Omfit profiles, transp, or 1-2. So as I just described, transp knows about the other physics modules. And so as one goes through a kinetic equilibrium reconstruction, transp will get the equilibrium from EFIT time, and it'll get the profiles from Omfit profiles. And you won't even have to hardly click on the button. It'll set it all up for you exactly as I showed. It'll set it up in kinetic EFIT mode. It'll run transp. It'll wait for the transp run to finish, and you continue on your iterations of equilibrium and profile reconstruction. So that was a good segue into how trans fits into other things. So that's just one example. That's kind of beyond just the basic trans tutorial. Are there any other questions about how the tool works or what the goals are or how it can be used? No?
Be specific. One, I think it was like a triage report says you need to increase beam ion diffusivity. or the fast ion diffusivity beams.
Okay.
How do you do that?
Oh, okay. I know what you're talking about. Okay, so this can happen. One of the things about tokamaks that have a lot of energetic particle and fast particle transport is that if you don't provide an anomalous means of redistributing the fast particles, that the fast ion density can actually exceed the electron density. And so you know that's not physical, right? That's not possible. So you know that there's got to be some fast ion transport occurring. And the way you can do that is to, in your transp run, as I open this up, under the input name list.
I suspect the transp is smart enough not to make the fast ion density too large. Combination of fast ion plus impurity density.
We'll make the deuterium density negative. It'll make the thermal deuterium density negative. Yeah.
By quasi-neutrality.
Yeah. That's correct.
At which point it stops the.
I step in.
Please.
So I think that TRANSP will not give you a negative deuterium density. What it does, it will adjust your recycling source so that you satisfy particle balance and quasi-neutrality. So what you can get a negative recycling source that you know it is unphysical. So you know that some of the other assumptions are not physical.
Okay, thank you for the clarification.
But ultimately what you're saying is TRANSP recognizes when it's doing something unphysical, stops the run, and emails you.
That's correct. Yeah, that's true. All right, so we're about to get kicked out of here. But if you go under heating, you can click use anomalous diffusion. And down here, you can set this value to something like 2,000 or 4,000 square centimeters per second. And that can fix it. Okay, I think, are we done?
If you're done.
I think that we're done. So that's the most basic way of performing transp runs and visualizing the inputs and outputs, and understanding how to do power particle momentum balance on tokamaks. So thank you.
Thanks, Brian.
Thank you, Brian.
Sure. You guys have a table layout in here for another meeting?
She's here for help.
It's the day cap.
We have this
Oh, yeah, okay.
booked till 5 or something.
Yeah, exactly. It's a good convenient time. You know, come up here. Oh, yeah. Yeah. I got everyone captured.